All right, guys, welcome back to the second part of section 8.4. We're still working on binomial expansion. You just turned in a homework or took a comprehension quiz where you were using some of the patterns you saw in the exponents along with Pascal's triangle to get the coefficients. And that made it, I don't want to say easy, but manageable to find a binomial expansion of something, say, to the fourth or the fifth, maybe even the sixth power. Today we want to look at an alternative way to find the coefficients other than Pascal's triangle, and this methodology works really well when the expansion gets to a power higher than, say, 6, 7, or 8, where, going down to that far on Pascal's triangle becomes kind of cumbersome. And what typically will happen is the book won't ask you to maybe do the entire binomial expansion, all say 14 terms of something raised to the 13th power, but they'll ask for a very specific term. But today we're going to look at a mathematical operation that comes from the probability world. Again, that same section of your calculator that we worked on before with factorial. It's going to involve factorial as well. That's why we did that little lesson on factorial before we started section 8.4. So a trick, it turns out, to find coefficients to a binomial expansion is to use a mathematical operation that they call a combination. A combination is a variation on a permutation, and you'll study both of those if you happen to take a stats or a probability class somewhere down the line. There's two ways to write a combination. It looks like almost like a foreign language, but it has very definite mathematical meaning. You can see here that there's two ways to write it. They both equal the same thing, involving some factorial. So it's you could say it is either NCR, and some people would say that is N choose R. That's how your calculator will have it, and that's how I'll try to write it more often than not on tests and quizzes. It also can be put as a fraction inside of parentheses, N over R. And then what they both mean and what they're both equal to, you can see here is this formula right here, where you do n factorial over n minus r factorial times r factorial. Now it looks really complicated, but it's not as hard as it would seem, and we'll go through a few examples here. We'll do it without a calculator, and then we'll take a quick time out and we'll show you, or at least verbally show you how to do it on your calculator. So if somebody asks you to do the combination of 9 choose 3, you would say, okay, that must be 9 factorial over 9 minus 3 factorial. That's where the n minus r is. So 9 minus 3 factorial would be 6 factorial, and then r factorial is 3. The 2 on the bottom will always add up to equal the 1 on the top, obviously, because n minus r plus r is equal to n. And what you're going to want to do is use your knowledge of how to do factorial to simplify this. Now, I saw some of you on the quiz and homeworks where you wrote the entire thing out, and we want to try to avoid that. So look at 9 factorial over 6 factorial and realize that everything would cancel except for the 9, the 8, and the 7. Okay, 6, 5, 4, 3, 2, 1 all cancels out with the 6 factorial, leaving you with only 3, 2, and 1 in the denominator. So what you might do is look to reduce. Again, I saw in the test and quiz some of you multiplied out the whole numerator, the whole denominator, and then tried to do a big, ugly, long division problem. You want to kind of simplify the best you can. So 3 goes into 9 3 times, 2 goes into 8 4 times. Now you've got the denominator, where it's just 1, and all you have to do is 3 times 4 times 7. And 3 times 4 times 7 is 12 times 7. That's equal to 84. So you can see it's very doable even without a calculator. And we'll do a couple more here, and then I'll show you how to do it on your calculator. But again, look for all the canceling you can before you do any sort of computation. The 9 factorial over the 6 factorial, almost all of it canceled out except the 9, 8, and 7. Then see if you can cancel anything from the numerator to denominator to make your multiplication easier. Okay, let's take a look at this second one. Okay, written differently than the first one, but it's done the exact same way. So you would do, numerator is 12 factorial, and then denominator would be 12 minus 2, so 10 factorial over 2 factorial. Now again, if you think about 12 factorial over 10 factorial, everything's going to cancel except the 12 and the 11. 10 on down to 1 will cancel with the 10 factorial in denominator. You got 2 times 1, And again, obviously, 2 times 1, 2's could cancel here. 2 into 12 goes 6 times, and you could say that this is equal to 66. So even though it looks kind of ugly to begin with, a lot of times it's a very manageable answer to finish with. Okay, this last one is about as hard as I would say I would make it on a non-calculator test. Obviously, it's very easy to do when you plug it into a calculator, but for non-calculator, this is about probably as high of the numbers as I go. Okay, so again, you would go 15 factorial up top. 15 minus 4 would be 11 factorial, and 4 factorial. So again, 15 factorial and 11 factorial, everything would cancel except the 15, 14, 13, and 12. Down below, you would have the 4, 3, 2, and the 1. Now, there's a lot of different ways to try to cancel here. You want to be as clever as you possibly can to get numbers manageable. You could, for example, cancel the 4 and the 3 with the 12. So many different ways to do this. It's really just kind of how you see to do it. And again, you should practice without running to a calculator. I would have probably done something like 4 goes into 12 3 times, maybe 3 goes into 15 5 times, 2 goes into 14 7 times. Still not going to be easy. I still have to kind of figure out what those 4 numbers multiplied together are, but you know, it can be something like 5 times 7 is 35, and 3 times 13 is 39. So you're going to have, whoops, you're going to have 35 times 39. And, you know, again, that's about as hard as we would make it. You go off to the side and figure it out if you wanted to. Multiply them together. So again, that's just equal to, did it off to the side on a piece of scratch paper, it's 1,365. So that's a little bit of a stretch in terms of maybe a non-calculator question, but that's about as far reaching as I could go. So let's take a stab at this with a calculator. So grab your TI-84, and it's going to be very similar to doing factorial. You're going to go to that same math menu, and again, activate the probability feature off to the far right. So scroll over to the right until you get to the PRB, and you'll see NCR is option 3. It's one above the factorial. So you don't need to use the factorial at all. You can use the NCR button on your calculator. Again, you'd have to tell the calculator ahead of time what you want for N and then CR. Depends on what version of the TI-84 you have. Some of you will get to plug it right into the holes or the boxes and it'll look perfect. Others will have to, on the older versions, put in the first number, then activate the probability menu, put in the second number, and it'll actually still have the NCR in between. So if I was going to do that on my calculator, it's kind of an older version, I would go 9, math, scroll to the right to probability, choose option 3, and then I would plug in a 3. And on my calculator, it says 9 NCR 3. Some of you newer ones, you should be able to plug it in where the 9 goes exactly where the N should be, and the 3 goes where the R should. Go ahead and hit enter, and you're going to get the 84 that we just got. Maybe skip the second one and practice with the third one. 15, math, probability, choose option 3, put in the 4, and hopefully we'll get that same 1365 that we had before. Okay, so that's real quick how to use that operation, how to perform it. Now let's see how we can use it to help with binomial expansion. Well, it turns out that the coefficients in binomial expansion are NCRs. They are very specific to that mathematical operation. You just have to know what to plug in for N and what to plug in for R. I think the easiest thing to do is just use N as being the power of the binomial that you're expanding to, and then have R be the power of the second variable. And that's kind of the key concept that I'm saying right here. The key concept is to recognize that the power of the second variable is always 1 less than the one you're on. So if I'm doing the first term, for example, my coefficient would be 4, choose 0 because I'm on the first term, so the second variable is going to have a 0 power. And I'll ignore the variables for right now. The second term would be for choose 1. Second term would have 1 as its variable. The third term would be 2 as the second variable. And you can see it just kind of continues on in the same pattern until you get to the last one where it will be 4 choose 4. So you can see the 4 stays consistent as the exponent, okay? N will always be that first number in the N choose R. The second number is always going to be 1 behind the term you're on, and it will always match the variable, the second variable's exponent. So 4 choose 0, let's do each of these kind of separately, would be 4 factorial over 4 minus 0, so 4 factorial, 0 factorial. Well, that's just going to equal 1. Because 4 factorial over 4 factorial is itself. And you knew that all along. The first coefficient is a 1. I'm just trying to show you how this actually equals and agrees with Pascal's triangle. This one would be, second one would be 4 factorial over 4 minus 1, so 3 factorial, 1 factorial. And 4 over 3 factorial, everything's going to cancel except for the 4. So you can see that one's going to be a 4. 4 choose 2 would be 4 factorial over 2 factorial, 2 factorial. A little more work on this one. You could say 4 and the 2 is 4 times 3 when you cancel out, and you got 2 times 1. And 4 goes into 2, so that's going to be a 6. 4 choose 3. Now here's where you can start to get smart here. 4 choose 3 is going to be the exact same as 4 choose 1. Because you're still going to be doing 4 factorial, it's just that you're going to do 1 factorial, 3 factorial. You can see that these second and the second to last are going to be the exact same numbers, and you recognize that when you were doing Pascal's triangle. So that's a 4, and then 4 choose 4 is 4 factorial over 0 factorial, 4 factorial. And again, 4 over 4 factorial is just going to be 1. Okay, so that is shows you that this is a legitimate option for finding the coefficients of a binomial expansion. And you can see that the 1, 4, 6, 4, 1 is the exact same thing you would have got from Pascal's triangle. Now you can throw in the variables and their exponents. Now you could say obviously it goes x to the 4th, x cubed, x squared, x, no x, nothing for y, y to the 1st, y to the 2nd, y to the 3rd, and y to the 4th. And what you're again going to notice is that these denominators match up with the exponents. So you got a 3 and a 1, power of 3 and 1, 2 and 2, 2 and 2, 1 and 3, 1 and 3. If I can I'll put the 1 in there for you. And then 0 and 4, 4. So there's a definite connection between the denominator of your factorial problem and the exponents on your variables. Again, if you're raising something to the 4th power, you probably wouldn't use this methodology. You'd probably go to Pascal's triangle really quickly and use it. But as you can see, we're going to get some problems where factorial and, well, Pascal's triangle wouldn't be as convenient. So as you can read here, the use of combinations to find coefficients in binomial expansion becomes much more valuable when the exponent gets large. And you can see an example here where there's a 13 and a 9 for the exponents on an expansion. Now, again, trying to find the 13th row of Pascal's triangle would take a while, and even the 9th is a little bit inconvenient, so probably wouldn't want to use that. You'll also notice that they only ask for a very specific term. In this particular problem, they asked for the 8th term, okay? So here's how I would do it. I would say, okay, you want me to find the 8th term? Then I'm going to do 13, choose, and we'll come back and figure out what number we want to put in there. In the A and B exponents, we know that if it's the 8th term, that this is going to be a 7th power. Remember, the power on the second variable is always 1 behind whatever term you're on, because it starts 0 power in the first term and then starts going up. Also remember that these two powers have to add up to equal 13, so we know that that has to be a 6, so that 6 plus 7 is 13. Okay, this here will always match the power of the second variable. So we know our exponents are going to be that. We just have to figure out what 13 choose 7 is. Okay, so that's 13 factorial over 13 minus 7, so that's 6 factorial, 7 factorial. Again, notice how the 6, 7 factorial matched up with your exponents. So this part's easy over here with the variables. Now we just say, okay, I would cancel the 13 factorial with a 7 factorial, so that would leave me with a 13, 12, 11, 10, 9, and an 8. Everything from 7 down would cancel. I got a 6, 5, 4, 3, 2, 1 factorial. Again, a lot of canceling here. You probably want to do as much as you can. Okay, for example, you could do 4 times 3 is 12. You could do, maybe that's the best thing to do here. I'll do that in a different color so you can see it. 4 times 3 is 12, so that cancels out. You could say that 2 times 5 is 10, although that's sometimes you want to leave the 10 up there. And then you could say the 6 factors at 3 and 3, so you got 3 left over there, 2 there, and then you could cancel the 2 with the 8 and make it 4. Again, that's not to say that that makes it easy, but all you have left is 13 times 11 times, so you really have 13 times 12 times 11. Again, probably a stretch in terms of doing that with or without a calculator, but it is certainly something you could do, and maybe there's even better ways to do the cancellation to make that easier. But we do know that the answer is going to have an a to the 6th. Again, I just kind of did that off to the side on a piece of scratch paper, and I got 17, 16, and we know it's a to the 6th, b to the 7th. Okay. So again, the concept of combining the power of the exponent to be the first number of your combination, using the pattern that you saw, that the power on the second variable is always going to be one behind the term you're finding, that the two exponents have to equal the original, so 6 plus 7 is 13. Then the real challenge was just doing that combination problem, which again was a little bit of a challenge, I'm not going to lie. And some of this will be calculator, some of it won't, but again, that's probably about the extreme stretch of how far I could go with a calculator. All right, let's try another one. Find the fourth term of x minus 2y to the 9th. Well, let's see, fourth term means that we're going to do 9, choose, we'll hold off on that part. Okay, let's try to get the variables in here so we know we're going to have x raised to some power and 2y raised to some power. If it's the fourth term, we know we want 2y to be to the third power because it's always one behind, which means this has to match up there. And again, the two powers have to add up to equal 9, so this one would have to be an x to the 6th. So 9 choose 3 is a little easier than the last one we did. So 9 factorial over 6 factorial, 3 factorial. That would be 9 times 8 times 7 over 3 times 2. Again, we may have done this one earlier. 3 goes into 9 3 times. 2 goes into 8 4 times. So we have 12 times 7, we have 84. We can see that it's x to the 6th. And then that's going to be careful here, 8y cubed. Don't forget to cube the 2 as well. So the last thing we have to do is multiply 8 times 84. Let's see, 8 times 80 is 640 plus 32. Looks like about 672 if I do that right. So our final answer is 672 x to the 6th y cubed. Again, if you're doing this and you're trying to do it as I'm suggesting without the aid of a calculator, you can always go back and just double check, do 9 choose 3 to see if you do get 84. Keep in mind you do have to raise the whole base to the power. Now the last thing we have to do on this problem is decide, is the answer positive or negative? Because it was a negative. So we just think to ourselves, we know it alternates from positive to negative, so all the odd terms are positive, all the even terms are negative. Since we were looking for the fourth term, we'd have to finish this problem off and say that the answer must have been a negative 672, x to the 6y cubed. Again, we know that it alternates between positive and negative, so the even terms are going to be negative and the odd terms are going to be positive. All right, here's one that we would maybe see on a calculator test. It says, use your calculator to help find the coefficient of the term with a to the 6th, b to the 5th in it. All right, so we know that we are going to take 2a, which is the first term, and since we need it to have a 6th power, it's going to have a 6 on it. Then negative 5b, and we'll put it in as 5b. We'll decide if it's positive or negative later. Would have to be to the 5th power, okay, in order to get a b to the 5th. Okay, so then we'd say, all right, we need to do 11, choose 5. Remember, this number and that number always match up. And when you do that, if you were going to do it out long ways, it would be 11 factorial over 6 factorial, 5 factorial. And you'll notice again that those numbers in the denominator are the same as your powers up there. So, again, use your calculator this time and just go 11 math probability option 3 and put in a 5, and you'll get that this part here is 462. Okay. Now you will have to figure it out from there. You know you're going to get an a to the 6th, but 2 to the 6th power is 64, and 5 to the 5th power, since you're working on a calculator, is 3,125. So now multiply all that to, whoops, forgot to do the b to the 5th. And now you just multiply all those numbers together. So 462 times 64 times 3125. And you got a really large coefficient here, which is obviously why this would be on a calculator only test. Okay. And again, when you get to numbers that big, it would have to be on a calculator test. And you can see why, again, when you start raising things to an 11th power or a 9th power or a 13th power, that this other way of finding the coefficient is probably advantageous to doing Pascal's triangle down to the 10th, 11th, 12th, 13th row. It's a little bit of a cumbersome when you get that far down, and likelihood you'll make a mistake. Okay, hopefully that helps, guys. And if you have any questions, obviously see me before you turn in this homework, which is due, we'll make it due on Friday. Give you an extra day to do it, and it's probably going to be our last section. We'll do one more quiz before the end of next week, but I don't think we're going to have quite enough time to finish everything that we were set out to do. So we're going to fall a couple sections short, but given everything we've been through, I think that's acceptable. Okay? We'll talk to you soon.